thing and glue it together, right? Is that the kind of model we're talking about? What kind of model am I talking about here? What kind of model? So we're going to model it mathematically. We're going to get to do word problems and make our own word problems based on the information we have in front of us. So now we're talking about energy and power, right? So what is it about energy and power that we love? Yeah. We can get stuff done. Good today. All right, so we get stuff done. What again are the units for energy? Joules. Joules. What's joules break down to? Who said joules? All right. Here. All right. So what is it again? Joules equals what? Joules is Newton meters. We got Newton times meter. What's the Newton again? Say again. Kilogram meters per second squared. Right? And that's energy or work, right? Because energy is the ability to do work. What's power?
Work over time.
Work over time. We can differentiate work, dW dt, right? Or we can simply say work over time. And so what are the units again then? Quickly, yeah. Watts or joules per second or joules per second. Right, so I got, all right, work over time. Now, what else is power? Because work over time, go ahead.
Force times velocity.
Force times velocity. There's a really cool animated slide that shows that too. So power force times velocity. Yeah. What else is power? Equals for 2 hours of charge. Times volt. I didn't abbreviate voltage with a V because then you would know if I meant velocity or what's the other one? Volume. It could have been volume, okay? That's where it can be, right? Is an answer. But you knew I meant velocity, right? All right, so what's the velocity equal to? What is the velocity we care about? Stay here. What is the velocity we care about? This one's worth chocolate. How fast our tool moves through the workpiece. What do we usually call that? WPI, no name tag. Surface speed, right? So we call it surface speed and we measure in feet per minute. All right, so V equals you just can't see it. But in any other web browser, you type YouTube at the top, it goes to YouTube, right? But not in Explorer. It searches for YouTube at Bing. All right, so what am I going to search for? Got it. happening here? Yeah, so there's relative velocity between that workpiece and the cutting edge of the tool, right? So there's a chip forming on the edge of the tool. Right? The top surface of the tool, where the chip forms and slides along, that's called the rake face of the tool. Top surface of the tool is the rake face. All right, so top surface of the tool is the rake face of the tool. What causes so the tool is feeding in this direction, or alternatively, the workpiece is feeding in that direction, right? But what causes that chip to form on that rake face of the tool? How thick is the chip? About 8 thick. Calibrated thumbnail there. So how thick is the chip? The thickness of the chip before, you can say it depends. It's before we made it or after we made it. Would you believe that when we put energy into the material to form the chip, it changes dimensions? Would you believe that we swoosh it or it expands? Yeah. All right. So we've actually got two thicknesses that we care about for the chip then. We've got an uncut chip thickness. We're going to call that T1. Back to this one. With an uncut chip thickness that we call T1. Uncut chip thickness is T1. How thick is T1? Think about what you know of the physics of the process. What's it going to depend on? So there's going to be forces applied, but the thickness of the chip doesn't depend on the force. The thickness of that T1, oh, but you don't have to have the right answer today, right? You just have to have an answer. So it depends on the width of the chip depends on the depth of cut. So the width of the chip depends on the depth of cut. The thickness of the chip, it depends on the feed rate, and it depends on the units you use for feed rate. What are the possible units we can use for feed rate? Anybody remember? We talked about this first week. Go ahead. Inches per tube and inches per revolution. Since we're doing a turning operation here, which one do we want to use? Inches per revolution. So we care about inches per revolution when we're doing a turning operation. And so our uncut chip thickness equals the feed in inches per revolution. Could be millimeters per revolution if we want to use scientific units, right? Except it doesn't always equal that. If the tool is skewed in this direction, so we can orient this tool any direction, right? Within reason, we can orient that tool in any direction. If the tool is not perpendicular to that surface, then the T1 equals feed times the cosine of that side edge cutting angle. So it equals feed times the cosine of the side edge cutting angle, and I'm going to call that beta. What's cosine of 0? 1. So when there is no side edge cutting angle, when that angle is 0, then our cosine is 1, P1 equals to P. All right, so as we're making our chip, we have a tool. So we got a turning operation just like the one we were just looking at. So I got my tool moving through the workpiece material, right? The chip, so this is my uncut chip thickness, right here. That's my uncut chip thickness, that's the feed times the cosine of the side edge cutting angle. What's bigger? The cut's bigger, right? That chip thickness is bigger. We've got tool, we've got workpiece material. That's the surface we just made on the workpiece. There's the original surface of the workpiece. And by original, I mean just before the tool got there. And we've got a chip flowing up there. Does that make sense? That diagram showed this, except I rotated it 90 degrees. Right? Really cool. You can watch me rotate 90 degrees over here too if you want to. So this is a model of the chip forming on the edge of the tool then. That's a model of the chip forming on the edge of the tool. Uncut chip thickness. This is my chip thickness. Here's my uncut chip thickness, my chip thickness. Now, why do I care again? Why do we make a model? Why do I care? Where did we start this discussion? We might want to know the amount of power the machine is going to need to cut the part. We've got a method. We talked about a method yesterday for estimating the power it takes to do a cut, right? What was our method again? So just quickly, you don't have to remember the details. Just quickly tell me what it is we're going to do if we want to estimate the power it takes to make the cut. Good, Xavier. Well, that's how we can measure the power that it actually took to make the cut. What if we wanted to estimate it before we get to the machine? Right. So we need to know material properties of the workpiece. We need to know what else? The shape of the tool and what material it's made out of and how sharp it is. I'll try again. Right? What else?
The effects of heat expansion?
Yeah, we may need to know something about what's going on there. We need to know the friction inside the machine tool. We've got all these factors, right? We can look those up. Where are we going to look them up? Machinery's handbook. It's got these charts and tables and equations, and so it can help us estimate the power that it takes to make that cut. Now, I know the power now, so I know it's going to take 6 horsepower to make the cut. Okay? Oh wait, we can convert horsepower to watts, right? Anybody know how to convert horsepower to watts? Okay, Google. How many watts is 1 horsepower? $745. There you go. We can convert from horsepower to watts, right? Good. All right. So 6 horsepower to make the cut. We're going to assume that if we're within the parameters that the tooling manufacturer told us we can use for that tool, that the tool is not going to explode when it absorbs 6 horsepower. Okay? I mean, because we might want to know how much power it takes to make the cut, so we can figure out what the force is on the tool to decide if the tool is going to explode. That'd be a reasonable thing to do. We're going to assume the tooling manufacturer figured that out for us. Why else might we care how much force it takes to make the cut?
The more important things about the top.
Yeah, maybe. I don't really care about that.
It's very close to very chances cracking the material.
So we may damage the material. Good at this. We may damage the material beyond its capacity, and we may cause the material to break, not in the place we intended to make it chip. That's a problem. What else? How do we hold our material in the machine? Up there, you get a hand up. You know the answer.
The vise.
We hold it in a vise frequently. It's not the only method. There's no vise. All right, so we've got a vise. Look at this. I came prepared. A vise. So imagine that we clamp our workpiece in the vise. And then the cutting force, now, so in the lathe, it's not clamped in a vise, right? It would be very awkward to have this spinning around at 6,000 RPM, right? Well, we're clamping it still, right? We're clamping it with those jaws of the chuck, or the collet. If it goes in that collet, it gets compressed down around it. So we're still clamping it as if it was in a vise. So cutting force goes on the tool, right? Pushes on the tool. Also pushes on the chip. That's what makes the chip form. So those forces are equal and opposite, right? Those damn laws of motion. The friction force between the workpiece and the vise has to keep the workpiece from moving. Do you agree? So how do we change friction force? How are we going to change friction force? If I get more cutting force, how do I get more friction force? Went tighter. Change the normal force, right? If we want more friction, we need more normal force. We can also change the friction coefficient, but that's the only thing we can change. Okay. So we have workpiece. There's our workpiece in the vise. Workpiece is very little friction. So it's problematic if we deform the workpiece when we clamp it in the vise, right? Yeah, it can be problematic. All right, but we would like to understand how the chip forms on the edge of the tool. So that one, we can understand the forces involved, and we can then assume that maybe all that force is trying to move the workpiece. So we can do an experiment. You can do this at home. No special tools required. You can use a knife. So we form our chip. We see a chip form, so we need to zoom in. The wrong direction. Even I know that's the wrong direction. There we go. Let's try again. We can make a chip. Yeah, this was a pretty good chip. It's in my pocket on the way. It's pretty hot. This one we were thinking about. You can see my daughter because of my YouTube channel. Don't judge people's suggested videos. I heard that's a rule. It'll make another pass. We've got our cutting tool, we've got our incremental depth, we've got our velocity through the workpiece. The chip form that flows up the rate face of the tool. All right, so we wanted to know about, we know that power here. I got my tool, I got my chip, I got my velocity. I might need to zoom out. All right, focusing. Good. Power equals force times velocity, right? What direction does the force have to point for this to work? This will be aligned with the velocity, right? You're actually doing a dot product. The force from the tool on the chip is this direction. We're going to call that the cutting force. Is that the only force on the chip? What else have I got? What else? So the tool is cutting. Where? Go ahead, up there in the back.
You have compression from the
Yeah, that's not acting on the chip. We are compressing the workpiece. Ooh, that almost took your head off. We are compressing the workpiece with the device, but that's not acting on the chip directly. So what else is going on here? Because they're equal and opposite. Right. That chip is moving, right? We saw in the video, the chip moves. The chip is moving in this direction. Right? Along the rake face of the tool. So if I push something on something else, because would you believe that that tool and that cutting force is pushing the tool on there? Yeah. There's a friction force because that chip is sliding along the edge of the tool, right? So I have a friction force. It's acting in what direction? Opposite the direction of motion. So there's at least a friction force here. We'll call that F. Amazing. What else is going on? So I get some cutting force going on. I get some friction force going on. What else is going on? Yeah, there's going to be a normal force to that friction force, right? And so that's going to be this way. We're talking about the force on the chip. Get some normal force out that way somewhere. What else is going on? It's going to be this way. What else is going on? The chip doesn't just happen, right? Because when we estimated our power, we had to figure out something about the material. Where does the chip happen? Over here we got material. Over here we got material. What happens in between? Right there. We have to physically change the internal microstructure of the material. Right? We have to do work on the material itself. There's stuff going on in here. And there's a force that lines up with this shear plane. So it's shearing at that plane right there. There's a force that lines up with that shear plane. Fs. So let's look at this. We got let's forget about the normal force for now. Here's the forces going in to making the cut happen. Then we can estimate this. We know F, so we know power. So we can estimate what this force is. Right? But what's really happening here is we've got this force, we've got our friction force going on, we've got our normal force going on, and those all add together to some resultant force. And our resultant force is going to be somewhere in this direction. We're going to call that P. And we've got all these different planes of geometric planes, these different things that we're looking at here. So I got my workpiece here. I got the tool. We're looking down the cutting edge of the tool in our picture. We're looking down in our picture. We look down the cutting edge of the tool right here. That chip is flowing along here, forming off. We'll pass them around. That's the up on this. Take a look at the geometry of what's going on here. What do we like to do with forces when we're adding them and subtracting them and stuff? So I know something. If I know something about the material, then I can know something about the shear force. If I know something about the power it takes to make the cut, I can know something about that cutting force. Now, turns out if I take my cutting force and I add to it a thrust force, those two add together and equal P. If I take my friction force, which is going to line up with this rake angle here, and I take my normal force, those two, that looks like a D. Those two add together and equal P. If I take my shear force and I take my force normal to the shear angle's drawn in the wrong direction here. My shear angle must be this way. Should come over there. Take my shear force and my normal to the shear. Those two forces add together and equal P. We've got three orthogonal force systems. The model that we're using here, we're calling this the orthogonal cutting model. We call it orthogonal cutting. So I've got a cutting force and a thrust force. They add together to make P. I've got a shear force and a force normal to the shear. They add together to equal P. I've got a friction force and a normal force. They add together to equal P. So if I have three orthogonal cutting, three orthogonal force systems, I can move from one to the other, right? The thrust force, cutting force P. I got friction force. So that friction force, we've got to have a mu, right? We've got to know something about the friction coefficient. How do we compare the friction coefficient? You had to do an experiment to find friction coefficient. What would you do? So how do you experiment or no experiment? How do you know friction coefficient? So it's going to depend on the two materials that are sliding against each other, right? What factors do you think influence the friction coefficient? So I'm just saying in general. So if we're looking at the friction of, this stuff on the table. Not everything on the table has the same friction coefficient, right? So what factors influence friction coefficient? So the roughness is going to influence it. What else? Lubricants will affect it. Like the stuff that comes, the white stuff that comes down in the winter, is the friction coefficient between your tires and the asphalt, right? The mass affected? Well, in this case it did because it affected the normal force, right? Right. So the normal force is going to affect it. It turns out temperature affects it. Because what's the temperature do? Yeah, I'm not going to put the cap back on that. Well, temperature is going to affect the material properties, right? We found that my butter at high temperature didn't have a very good friction coefficient because I couldn't clamp it very good. Yeah. As the materials change, the material properties, you might want to watch out there. The material properties change, right? And so we can't actually, to find out that friction coefficient on the ship sliding on the rake face, we can't just lift up the table and then calculate the angle at which it starts to slide. That's not going to work because there's very high temperatures going on. But we do know that that friction coefficient equals the tangent of the friction angle. We know the slide where we do the friction angle. And we also know that the tangent of the friction angle equals F over N, because it equals the friction force over the normal force. If we would like to get, if we know the friction angle, we can convert using Merchant's equation to find the shear angle. And so the shear angle is nice for us, because we know that shear force lines up with that shear angle. We can also find the shear angle if we know something about the geometry of the cutting operation. What's T1 again? Uncut chip, so uncut width of the chip would be the end of the board, and that's going to be based on the depth of cut. But our uncut chip thickness equals what? Nick. Speed times cosine of the side edge cutting angle. He's going to get happy. Right? So, turns out from geometry, and I went for an extra credit assignment in this class. I said you guys can have extra credit if you prove this statement here, that the tangent of the shear angle equals RT. RT is T1 over T2. Tangent of the shear angle equals RT cosine alpha. Alpha is the rake angle. That's how much that tool is tipped. Over 1 minus RC sine alpha. You remember, was it like 9th grade geometry class where you did stuff like this? Right, where you had to prove things? So I thought this would be a cool extra credit assignment. And before I could give the extra credit assignment, I actually had to do the proof myself. And it had probably been 25, 30 years since I had tried to do a proof. It took me about 3 days. I don't know how many dozen sheets of paper, but that's not what I'm brought out. But I got myself a nice proof. I said, all right, I can prove it. Put it out there for the assignment. Depending on how you state the problem statements, there's more than one way to prove that this is true. Which means every time there was a submission that wasn't equal to my submission, I had to figure out if it's correct, whether or not I gave them extra credit. So I've stopped giving this as an extra credit assignment. But if you had to, could you stand up right now and prove this? If you prove this, you would get an A in the class. Could you do it? Because all you had to do to get an A in the class was prove this. Could you do it? Stand up if you think you could prove it. I already told you it's true. I already told you people just like you in a previous term have proven it. Come on, there you go. All right, mark down Xavier gets an A. This is chocolate too. All right, but at any rate, so we can know what the shear angle is from the geometry of the cutting operation. If we know T1, T2, and alpha, how do we know what alpha is? We chose it. It was one of our process variables. We pick alpha when we stick the tool in the tool hole. So we pick alpha. How do we know what T1 is? We chose it. T1 is actually the feed diagonal. We chose it. It's one of our in a planing operation, it would be the incremental depth. Only in a planing operation, which is sort of what I was doing here. In a planing operation, we just sky something off the top. How do we have T2? T2. How do we know T2? There's worth 3 of these chocolate things. But you gotta have the right answer. I'm gonna hurry up, so I'll talk about 3 times. How do I know T2? Those are engineers? What? Google does not know what T2 is in this instance. It might know the method. I mean, it depends on the material and the increment, all that stuff. How do we know what T2 is? Because I'd really like to know what the shear angle is. Because if I know what the shear angle is, then I can figure out what that friction angle is. If I know what the friction angle is, then I can figure out what the forces are. Pick it up out of the bottom of the machine and measure it. We find T2 experimentally. We could also get it from measuring when we had that YouTube video going. This one. Oh, yeah, we can measure it here. Right? So if we did an experiment like this, we could put a scale in our picture, right? And we can measure it off the picture. So we can measure T2. Group assignment. And I'm going to change the due date for the group assignment. Group assignment will be due next Wednesday, not Friday. This week. So your group assignment due next Wednesday. And the group assignment. Oh, and I'm not going to do a quiz this Friday. Well, I am going to do a quiz this Friday, but it won't be due until next Friday. Okay? You'll have extra time to work on the quiz. Because the group assignment is to use Excel to create models for solving problems. We're going to make computer models for solving problems where I give you an input. For example, I tell you the feed rate was this. What's the uncut chip thickness? The feed rate was this. The sighted cutting angle was this. What's the uncut chip thickness? So I'll give you a list of possible questions that you'll have to answer with information like that. If this is given, and this is what we're asking for, create an Excel spreadsheet page that does that calculation. Then for another one, if this is given, so for example, say we give you the shear angle and the friction angle, I think you can calculate the cutting and thrust force from that based on the vertical rate. So you're going to use a collection of the equations that we have, and I have just for you guys a special, I think it's a Google Slides, it might be a PowerPoint. A special presentation is just a collection of slides of all of the equations that we present in the class. So that you don't have to go back through all the notes to figure out what all the equations that we present in the class are. Sort of a, what's the word? Reference guide. Not like cheat sheet. Cheat sheet implies that you shouldn't have access to reference material when you're doing hard problems. I like to memorize things, so I don't expect you to memorize things. We're going to have that group assignment next Wednesday, and it will include also questions from the type of questions for this Friday's quiz, which will be due next Friday, and from next Friday's quiz, which will also be due next Friday. And so you make a different make a little different tab for each question, and so you'll have a chance to submit that on Wednesday, and give you also some test numbers so that you can test to see whether you're getting the right answers. My goal here is that everybody can get 100% on the quizzes because you figured out how to answer the questions.
So we need to
yeah, I'm providing the list of the questions.
So I have Dev along with class. So, and plus like